All right, so we're going to start thinking about these molecules in three-dimensional shape. And so the first one we're going to take a look at is good old ethane. Very simple, just two carbons and some hydrogens. So remember, ethane we can just draw as a straight line, something like that, not maybe a little bit straighter than that. But don't forget that each one of these is a carbon, right? An sp3 carbon with then 3 hydrogens on each, right? So something like this, right? You see 2 carbons and then 3 hydrogens on each. And then don't forget we can also rotate about this bond, right? So we can rotate both sides. And so there's 2 main conformers we can draw here, right? We could draw these H like this, and then a dash H and a dash H, right? Both of these are tetrahedral carbons. And so let's go ahead and take a look at this. And so we can see this motif right here, right? We have this hydrogen, then the carbon-carbon bond, and then the hydrogen. So both hydrogens are sticking up. And you see in this model right now, both hydrogens are sticking up. And then we want to go ahead and take a look at this through a Newman projection. So we have our little eyeball right here, and we're staring down this bond right here. So if we go ahead and do that, you can see what it looks like, right? You can almost not see the back ones. And then in our Newman projections, we actually shift them a little bit. But then don't forget we can rotate about this bond. And so we could draw one where the 2 hydrogens are up like this, or we could fully rotate it where one of the hydrogens is now down. So let's go ahead and draw what this would look like. So we're just going to leave this guy alone. And then we're just going to put 1 hydrogen down, right? You notice the motif here now is this hydrogen is now pointing down. And then, of course, we have our wedge hydrogen and our dash hydrogen, right? And so that looks something like this, right? You see this hydrogen is pointing straight up, this hydrogen is pointing straight down, and then we've got one going in and out of the board, one going in and out of the board. And then, of course, we want to think about our Newman projection, so we'll put a little eyeball here, and we're going to stare down this bond. And so that would look something like this. So you want to go ahead and draw this Newman projection here and label it. And of course we can get intermediate ones, right? We could rotate these bonds the whole way through. But there's really only 2 main ones, right? When they're completely overlapped and about as far as away they can get, right? All right, next up, let's go ahead and think about butane. So this is 4 carbons long, 1, 2, 3, 4. Right, and this is the way we would normally draw it. If you think about the 3-dimensional shape, it looks something like this. You can see for these carbons on the end, I've put these short bonds here just to make it less cluttered, right? If I use all these long bonds, it gets quite cluttered quite quickly. But you can see I've got it in this kind of zigzag design. Right, you see zig, zag, zig. Right, and so we can think about our Newman projection here. So we can put an eyeball here and look down this bond. That would be this central carbon-carbon bond. And you can see this guy is pointing down, and so we want to keep it pointed down. And you can think about what this Newman projection would look like. But then remember we can rotate about this bond. And so we can rotate these atoms. Right, and so in this case, we'll just rotate the carbon in the back. And so we could rotate it something like this, right, until it's eclipse form, but we know that's not good. So we can go to the next best one, the staggered formation. But now you can see we've got this interaction right here. And if we were to think about what this would look like on a piece of paper, we see these 3 carbons are flat. Right, flat, and then there's 1 CH3 going into the back of the board. Right, so that's what that would look like. And then finally we can get one more conformer where we slide it over, and now they're totally overlapped with one another. And if we think about how this looks like on a piece of paper, it would look something like this. Right? They're all in the same plane of the board. And then, of course, we can actually keep rotating. right? But we can see that this interaction is going to look the same as another interaction, right? It's going to be another eclipsed version here, and then we're back to the original. So there's butane, also pretty simple. All right, so next example we're going to take a look at is 2-chlorobutane. And so this is a butane, 1, 2, 3, 4, with a chlorine on the second carbon. And so overall, this looks pretty simple, but it can actually be a little bit more complex than it seems at first. Because here on this carbon right here, we've got 4 different substituents. We've got a methyl, we've got an ethyl, we've got a chloro, and then of course we have a hydrogen. And so those are 4 different groups on this sp3 carbon, and so this makes it a stereocenter. And so there's some stereochemistry that's interesting here. And so there's actually 2 different stereoisomers, or a set of enantiomers for this compound. We could draw this compound with a wedge on this chlorine, or we could draw it with a dash on this chlorine. Right? Wedge, dash. And so that's what I've got here, right? You can see in this model, my chlorine is coming out of the board. You can see all 4 carbons are in the same plane, and this one is coming out of the board. On the right here, again, I have all 4 carbons in the same plane in this zigzag format. And then you can see that this chlorine is going into the back of the board. And so let's think about the Newman projections here. Again, we're going to take a look at this bond right here. Right, so this carbon-carbon bond and this carbon-carbon bond. And so first, we've got the wedge format, right? The chlorine is coming out of the board. And so if we take a look over here, we can see right now we've got the 2 methyl groups anti to one another, and we can move them around, right? Think about all the conformational analysis, right? Think about this one, is it good, is it bad? Think about that one, is it good, is it bad? Is this one good, is this one bad? Good or bad? And then kind of right back to where we started. And then we've got the dash format, right, where this chlorine is going into the back of the board. And so again, we can think about looking down this carbon-carbon bond, right, and then we've got the 2 methyl groups anti to one another, and we can move them around. Right, go back to our zigzag format. And so we've got our 2 zigzag formats, and then if we think about the Newman projections here, just lay them down something like that. Let's see, maybe I get a more overhead picture. Yep, cool. And so we can see that these 2 molecules are not actually the same, right? We have both methyls anti to one another, but this chlorine's going off to the right, this chlorine's going off to the left. And so if we rotate one of them to have the chlorines face in the same position, right, now the chlorines are in the same position, but the methyl groups are not in the same position. So you can see that these 2 molecules are different. And there's no way that I can twist or turn or really do anything to these molecules to make them the same. They're not the same molecule. Similar to your left and right hand, right? My left hand and my right hand, I can never put them over top of one another and have complete overlap, no matter what I do, right? This, yeah, it's technically complete overlap, but you've got opposite sides facing each other, right? You cannot superimpose one hand onto the other, just like you cannot do that to these pair of enantiomers. All right, so next up we're going to take a look at cyclopropane, right? So drawing this on a piece of paper, it looks like a triangle, right? Propane means 3. And then, of course, we can think about our 3-dimensional image of cyclopropane. So here it is, 3 carbons in a triangle. The first thing that you notice is that my bonds are quite bent, right? These little sticks are supposed to be straight, but you can see they're quite bent. And so you can see the angle strain in this molecule. And then if we think about it from a Newman projection point of view, just missing a hydrogen, right? If we take a look down these bonds, right, we can offset them a little bit, but they're still quite overlapping one another. And you can see that they're all overlapped. No matter which bond you look at, it looks essentially the same. And there's not really anything I can do in terms of twisting and turning to get rid of any of this strain. So you can see cyclopropane really is a strained system. All right, so next up is cyclobutane. That's 4 carbons in a cyclic structure. So essentially you got a square here. And so that's what we have right here. You can tell this is one conformer, in which case my square is quite flat, right? First thing you notice is that these bonds, again, they're slightly bent. Not as bad as in cyclopropane, but still pretty bad. And then if we think about the Newman projections, look what's going on here, right? We have direct overlap of all of these bonds. So my model kit doesn't really mind this, but in real life, these bonds don't like this. And so one thing we could do is we could push 2 of these carbons up or down, right? And so you'll see my model kit doesn't really want to do this because it doesn't have, the electronic interactions. It just has the bond angle interactions. But I can force it to do it. And so you can think the angle strain is actually worse here. We've actually bent our bonds a little bit more. But now if we take a look at the Newman projections, it's up here, you can see that we've relieved some of our strain, right? If you look at down all of these bonds, they're quite staggered with one another. You can see over time it doesn't really want to stay. Didn't buy the best model kit. But you can see the staggered versus if it's flat, the eclipsed. Alright, so next up we've got cyclopentane. 5 carbons, essentially a pentagon. And so here I have it in this kind of flat structure. You can see it's flat on the ground, so it's obviously flat. And so it doesn't look too bad here from the angle strain, but if we think about the Newman projections, there's a whole lot of eclipsing going on here, right? You look at any of these bonds, and they're all eclipsed from one another, right? My model kit doesn't mind that, but in real life, it does mind that. And so one thing we can do to alleviate a lot of this strain is to simply push one of these carbons up, right? Or up or down, get them out of the plane of the board. But not only does it change this carbon, it's also going to change the hydrogens on this carbon. So while these 2 carbons themselves aren't going to move, pay attention to what happens to this hydrogen as I move this carbon up. So as I move this one up, and to get it to stay up, my model kit's not the best, you can see that that hydrogen moved, right? Now it's kind of coming out. Whereas when it's flat, it's going up. And so when I push this up, it actually pushes these hydrogens down. And so then if I think about my Newman projection, now I don't have eclipsing. Or at least not to the extent that I did before. So you can see the advantages once we move on to cyclopentane. Not only the angle strain, but the torsional and the steric strain as well. All right, now moving on to the star of the show, cyclohexane. So 6 carbons. And so you can see here I have it in this kind of flat conformer. You can see that these bond angles are bent. And then if we think about the Newman projections, we've got all of this strain as well. And so this is overall not good at all. Really, what it adopts is the chair conformer. And so one of these carbons is going to go up, one of the carbons is going to go down. And when I do this, not only are these carbons going to change, these other 4 carbons, while they won't move, their carbon-hydrogen bonds will. So watch what happens when I do this. And my model kit's not that great, so I have to manipulate it a little bit more than I'd like. But you see when I move this carbon up, watch what happens to these CH bonds. You see, they change. And then I'm going to go ahead and move this one down and watch what happens to these CH bonds. Right. They change. And so here we've got our chair conformer. And so this is the way it kind of looks like a chair. Just exaggerate it a bit more. Right, it kind of looks like a chair right there where your person, this is the kind of headrest, and then this is like the leg rest, kind of like a lazy boy. So it looks kind of like carbon, 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 carbon. And then your little dude is chilling over here. right? So that's how it looks like a chair. However, that's not the way we draw it, right? The way we draw these chair conformers is more like this kind of bow tie type of setup. Right, like that, or like that. And so, right, how do we get from here to what we actually draw? Well, we just simply rotate it. So if we think about this carbon right here, that looks just like this structure, right? There's the Newman projection, but there's this structure right there, right? You see these 4 carbons are about in the same plane, and then this one's pointing up, and then this one's pointing down. And then if we reverse it a bit, here's this carbon right here, right? These 4 carbons in the same plane, this one pointing up a bit, this one in the back pointing down. So there's kind of how you go from this bow tie to what it actually looks like in 3-dimensional space. And so there's a number of things we want to take a look at here. First off, when we look from the overhead view, we can see that there's 3 axial positions facing up, and then 3 more axial positions facing down, and you can tell that these axial positions are much closer to one another than these equatorial positions, right? These equatorial positions are actually quite far, not just from distance, but if you also think about the bond angles, they're on opposite sides, whereas all these axial stuff are on the same side. Another thing to note is that all these carbons are the same. Although it looks like one is out of the plane and one is in the plane, they're all actually the same. So for example, here's the Newman projection right there. And then if you just move over, you get the same thing, right? It's just flipped. If you just view it from this way, it looks the same. Right? So all of these 4 carbons in reality are the same. There's a lot of symmetry in this molecule. And then if you're taking a look at these Newman projections as well, you'll notice that all of this stuff is staggered. Right? All these carbon-hydrogen bonds staggered. And so you can see how effective this chair conformer is. Next up, let's take a look at methylcyclohexane and its ring flip. So first of all, here's our model of methylcyclohexane. You can tell we've got 6 carbons, and then we've got this methyl group as well. And so the first thing you want to envision is, how does this bow tie look like this compound right here? And so the way it looks like this is like this, right? If you think about it, here's these 4 carbons are going to be these 4 carbons. And if you think about the Newman projection, this carbon up in the front is pointing up. So that's going to be this carbon right there. And then this carbon here in the back is pointing down. So that's going to be that carbon right there. And so that's how this model looks. And then if you think about this top-down view, you can see how these axial positions are going to start getting cluttered, right? If I made these long CH bonds and then these were also methyl groups, you can see how all of this stuff is going to start hitting each other, and there's just not going to be enough room for all this stuff to fit. Okay. Let's keep this color coding here. All right, let's see how we're going to do a chair flip. So when we do a chair flip, what we do is we move this carbon down and then this carbon up. We'll actually do it in reverse order. We'll move this carbon up first and then this carbon down. Right, so what we're going to do is we're going to move this carbon up. Notice when I move this carbon up, what happens to these CH bonds as well. Right, they flipped, you see? This guy's axial. Now it's equatorial. And this is what's known as the boat conformer, and you can see why this is not favored, right? Look up here. These things are slamming right into each other. So this is no bueno. This is no bueno. And so what we need to do now is we need to move this carbon down here, right? So we need to move this carbon down to get rid of this. And if you also think about this boat conformer, we've got eclipsing of these bonds as well. So there's a lot wrong with this boat conformer. Not wrong, but, you know, disfavored. And so now we're going to move this carbon down, and then at the same time, you simultaneously want to watch what happens to these CH bonds. Now my model kit kind of sucks, so I have to manipulate it a little bit. If you get a better one, it won't do that. But you can see that they switch, right? This carbon right now, kind of sticking out here, now goes into an axial position. Right, and you can see this methyl group that was equatorial, or was axial, is now becoming equatorial. All right, and so now if we think about it in the original way, right, this is kind of what it looks like. Remember that this bond is this purple one over here, and then this purple one over here is this purple over here, right? So we matched up our methyls. And so if you think about the Newman projection, it makes sense, but if you were to kind of draw this, it wouldn't really, it'd be hard to draw on a two-dimensional piece of paper, right? You could, again, kind of draw these two in the same plane, but now the back one's kind of coming up, and so it looks something kind of, you know, maybe something like this, I don't know. And then you can see that the front carbon is kind of going down. So you can kind of draw it like this, right? This isn't really going in and out of the board, more showing up and down. And you see how this is just very confusing to look at. So instead of looking at it like this, what we do is we just shift our frame point so this top carbon comes out to the front, right? This carbon right here becomes this carbon right here. So if we simply just rotate the molecule, we'll see it looks just like this, right? Where we've got these four bonds essentially in the same plane. But if you think about what they were actually these two bonds from the previous picture. No, not quite. Yeah, color coding is not really going to work. Use different colors. Right, so those are those two bonds, and then you can see this carbon in front is sticking up, just like this carbon in front is sticking up. And then the carbon in the back is sticking down, just like this carbon in the back is sticking down, and now our methyl group is equatorial. And then if we reverse the flip, right, move this back over here, move this back down, right, now we're back to what we were, right, with this carbon equatorial. But if you look at it from this point of view, right, it's confusing. How would you draw this? It's confusing. And so what we do is we just shift over. And again, we're back at this drawing. And so hopefully that clears up how these two chair flips make sense, right? We flip the carbons, and then we kind of switch. We rotate our position that we look through. That way it looks nice on a two-dimensional piece of paper. Next up, let's take a look at some stereoisomers. So over here I have a cis alkene, and then here I have a trans alkene. And so here's the cis alkene. As you can see, I cannot rotate this bond, right? It's a double bond. You can't rotate it. This isn't the best interpretation of a double bond, but whatever. However, the configuration of, or not the constitution of both of these are the same, right? You've got a carbon with 3 hydrogens and a carbon bond. You've got a carbon with a single carbon bond, a double carbon bond, and a carbon hydrogen bond, and then the same thing on the left. So to make this trans one, I have to switch these, but I didn't really switch the constitution because we still have a CH bond and a CC bond. But I did change the location of these bonds to make this trans configuration, right? And so at the end, these two are not mirror images of one another, right? They're not mirror images, but they're also stereoisomers of one another, and so we call these diastereomers. All right, next up, let's look at enantiomers. So we need a carbon that has a stereoisomer, right? So this is sp3 carbon with 4 different things attached: a hydrogen, methyl, hydroxy or alcohol, and then a chlorine. And then we have its enantiomer over here. So here's the two models, right? We can see the hydrogen over here, the methyl over here, the OH on this red coming out of here, and then this chlorine going into the back of the board. And then with this other model, we have the hydrogen, the methyl, now the alcohol going into the back of the board, and the chlorine coming into the front of the board. And so this drawing, they don't really look like mirror images, but they are of one another, right? So here's my hands mirror images. You can tell my thumbs are both down and close to each other, and then my index fingers are up and close to each other. So here's again our two models, and then if we simply rotate one of them, we see this mirror image right here, right? The chlorines are back there, the hydrogens are up there, and then if you think about it kind of from the classical view, it looks something like this, right? So you can see that they are mirror images, just like my hands are. And no matter what we do to these mirror images, we can never fully superimpose these, right? My thumbs aren't superimposed, none of my fingers are superimposed, and then if you do it like this, right, that's not superposition because they're on opposite sides, right? My hand, my palm, and the back of my hand are different. And so same thing if we try to match these up, right? Here we've got these chlorines and these hydrogens matched up, but now we've got a mismatch, right? These don't superimpose and these down here don't superimpose. And if you try to fix it, right, try to make these alcohols superimpose, now the methyl and the chlorine don't superimpose. And same thing, no matter which way you twist this about, you will never have perfect superposition. Right, now the hydrogen and the methyl, right? So they're enantiomers. They are indeed different molecules, just like my hands are different hands. And not only do you need to be able to kind of picture these in this conventional way shown, but you need to be able to rotate these around in your mind, right? If this is my right hand and I turn it over like this, it's still my right hand, and you still need to be able to recognize that. And the way we do that is with R and S. So I'll teach you the right hand rule next. All right, so the way we tell these difference, just like our hands, we have a right hand and a left hand. With these molecules, we have an R and an S enantiomer. And so let's take a look at the right hand rule. This is the way I like to do it. You don't have to do it this way if you don't want to. The first thing, though, we need to do is assign priorities. And so remember, the first thing we take a look at is the atomic mass. And so we can figure out all these just from the atomic mass. Chlorine has the highest, followed by oxygen, followed by methyl, and then the hydrogen. Right, and then same thing over here, chlorine number 1, oxygen number 2, methyl number 3, and then hydrogen number 4. And so for our right hand rule, the first thing that you got to make sure to do is use your right hand. Don't use your left hand, use your right hand. It's the right hand rule, you got to use your right hand. And so what you do is you stick your thumb up in the direction of the lowest priority, so in this case our hydrogen, and then you curl your fingers. And then you see if you go in correct numerical order. Do you go from 1 to 3? That's correct numerical order, right? That's R. Or do you go backwards? Do you go 3, 2, 1? That's not the way you count. And so in that case, it's S. And so let's go ahead and take a look at molecule at this on the right here. And so we have the hydrogen pointing up, the methyl pointing down, the chlorine pointing out, and then the alcohol pointing out, right? And it shouldn't matter how we rotate it. This is the way that it's drawn on this piece of paper. And so what we do is take our right hand and we place our thumb facing the hydrogen, right? The lowest priority. And then we curl our fingers. We curl our fingers. And so we see when we curl our fingers, we go from OH, methyl, to chlorine. So we go from OH to methyl to chlorine and then back again. If you take a look at the numbering system here, right, 1, 2, 3, that's correct numerical order, and so this molecule is R, right? So really it's over here, 1, 2, 3. 1, 2, 3. And then let's take a look at this molecule again in the orientation that is drawn. Here's the alcohol, and here is the chlorine. And then if we stick our thumb up, right, and then we curl our fingers, we see we go chlorine, methyl, oxygen. Chlorine, methyl, oxygen. Chlorine, methyl, oxygen. So we go chlorine to methyl to oxygen, and then the back around, right? And then if you're thinking about the numerical kind of thing here, right, we're going 3, 2, 1. We're counting backwards, so this is S. If you count backwards, you are S. If you count forward, you are R. And so you have to be able to do this no matter which way the molecule is oriented, right? If this is my right hand, I can flip it like this, it's still my right hand. Still my right hand, still my right hand, still my right hand, still my right hand, still my right hand. No matter what I do to my hand, it's still my right hand. And so are these molecules. No matter which way I twist this, it's still R. And so again here, right, this is not quite the way it's drawn, but right, 1, 2, 3. 1, 2, 3. That's R. And so here's just a bunch of different configurations this could be drawn in. So one way you could draw this molecule is have the hydrogen pointing out, the alcohol pointing back, and then the chlorine pointing out of here, right? And so when I'm doing this, right, I stick my thumb to the lowest priority so that the hydrogen is coming out, my thumb goes to the out. And then I curl my fingers. So you can see I'm going from OH to methyl to CH, or to Cl, and then back around. And if I number these, right, this is number 1, this is number 2, this is number 3. That's correct numerical order, and so it's still R, right? Just because I rotate it in space, it's still R. And so that's with the hydrogen pointing out. Another one could be with the hydrogen pointing in. Right now the hydrogen is pointing in. So what I want to do is stick my thumb into the back of the board, And so you can see if you look at this image, if I'm sticking my hand in the back of the board and I'm curling my hand, I'm going methyl chlorine oxygen. Methyl chlorine oxygen, right? And so here's the image right here, right? Thumb in the back, methyl chlorine, and then if I kept twisting my hand, oxygen. Right? Methyl, chlorine, oxygen. Right? Methyl, chlorine, oxygen. Methyl, chlorine, oxygen. Right? So stick your thumb wherever number 4 is and just curl your hands. If you're counting the correct order, it's R. All right, so we've got that scenario, that scenario, that scenario. And then the final scenario would be with this hydrogen pointing over here. And so in this case, we'd have this hydrogen here, this methyl group sticking out like this OH here, and then this Cl here. Again, what I want to do is stick my right hand wherever my lowest priority is. So in this case, it's the hydrogen, and then just curl my fingers. I'm going chlorine, oxygen, methyl. Chlorine, oxygen, methyl. Right? Chlorine, oxygen, and then the whole way around, methyl. Chlorine, oxygen, methyl. And again, this is 1, 2, 3. It's still R. So you see with the right-hand rule, once you can picture this image in your head, all you got to do is just stick your thumb up wherever the lowest priority is and curl your fingers and think about if you're counting in ascending order, right? So if the lowest priority is pointed up, go like this. If the lowest priority is pointing up, go like this. If the lowest priority is pointing in the back, go like this. And then if the lowest priority is off to the left, go like this. And then same thing for the S, except here you'll count backwards. You can also use your left hand. Your left hand will go correctly with the S, but I don't like using both hands. I find, it's easier if you just use one. If it fits, it's R. If it doesn't fit, it's S. And so that's something that you really want to get good at. You don't have to necessarily use my method, but honestly, I think my method is the best. It's not my method, but this method I think is the best. All right, let's continue our look into stereoisomers, and then let's take a look at an interesting case of 1,2-dichlorocyclohexane. And so I have the skeletal structure drawn right here. The first thing that we want to realize is that these are indeed stereocenters. So let me show you this. Right, we have a hydrogen here, so that's one group. We have a chlorine here, so that's obviously a second group. Here we have just a regular alkane, and then over here we have a halo alkane. So that's 4 different things attached to it. So this is indeed a stereocenter. Right, this right here is a stereocenter, and this is the same thing, right? So this is a stereocenter as well. And so if we have two stereocenters, we should have 2 to the n number of stereoisomers as a max, right? So 2 to the power of 2 is equal to 4. So 4 maximum stereoisomers. So let's go ahead and take a look at some of these stereoisomers and the relationship to one another. So one way we could draw this is with a wedge up here and then a dash over here. Or we could do the reverse and dash here, wedge here. And let's go ahead and draw the chair conformers of this as well. So whenever you're drawing the chair conformers, you want to count 1, 2, and then if you're going clockwise, you need to go clockwise here as well. It doesn't matter where you start it, but you have to go clockwise. So this will be 1, this will be 2, and then we'll have a chlorine up, because this hydrogen here is down, and then a chlorine down, like so, because this hydrogen here is up. And then let's draw this structure in the same configuration. And we'll use the same numbering scheme, 1, 2, 1, 2. However, now this chlorine here is down. If you think this is up, so this is down. And then this chlorine over here is up. If you think about it, this axial position is down, and so this position is up. And so we've got two different structures right here, or two different looking structures at least. We'll see if they're actually different. One thing we can do is assign R and S to them. So you can do that with either one of these structures. You can use this one, you can use this one, you can use a 3D model, you can do whatever you want, right? So remember that there's a hydrogen back here. This hydrogen is here, and then you want to number everything, right? Chlorine gets number 1, this haloalkane gets number 2, and then this alkane gets number 3, and then hydrogen gets number 4. And so if you think about this is R or S, stick your finger in the back, right? Because the hydrogen's in the back, and then curl your finger, right? Look, I'm going from chlorine to the haloalkane, and then finally to the methyl. That's 1, 2, 3. And so this is R. And you get the same result down here, right? My thumb's to the hydrogen, here's the chlorine. Then I come to the haloalkane, and then finally when I would be twisting back, I'd get down to the regular alkane. So 1, 2, 3, again, that's still R. And then here is a model of this, right? This is the way it looks. You see we have these 4 carbons, are these 4 carbons. This one's sticking up front, this one's sticking up front, this one's sticking in the back, this one's sticking in the back. So it looks kind of like that. We can see our chlorines are axial here, just as was drawn here, and that this one is up, and this one is pointed down, right? And this hydrogen is down, this hydrogen is up. And so again, if we take our thumb, right, curl our finger, chlorine 1, then to the haloalkane 2, and then finally in the back of my hand, the alkane 3. So again, this also shows us that it is R. And then if we take a look over here, we have this hydrogen here, and again we want to go ahead and number. Chlorine gets number 1, the haloalkane over here gets number 2, this alkane gets 3, and then hydrogen gets 4. And so this time I'm going to stick my thumb out of the board, and you can see I go from chlorine to haloalkane to methyl. 1, 2, 3. So this one is R as well. So they're both R. And you can also see that with this structure right here. Stick my thumb out here because this hydrogen is sticking out here. This CC is a Cl, of course. And so if you think about it, where am I starting from? I can start at this chlorine, and then if I continue to curl my thumbs somehow through my hand, I'd come up to the haloalkane and then to the methyl, right? So it's kind of like 2, 3, 1, which is the same as 1, 2, 3, right? We're counting in ascending order. And so again, this also tells us that it's R. pick a different color for this. Red, I guess. No, blue. R, R. And we have it drawn, or we have the model right here. Let's go ahead and take a look at this stereoisomer. Again, we want to think about whether it's R or S. So we have a hydrogen in the back here, or in the front here, as a wedge. And then we want to go ahead and label or rank our substituents. So the chlorine gets number 1, the haloalkane gets number 2, the regular alkane gets 3, and then the hydrogen gets 4. I'm sticking my thumb out of the board because that's where the hydrogen is. And you can see now I'm counting 1, 3, 2. That doesn't make sense, right? I should go from 1 to 2, not 1 to 3. So this doesn't fit my right hand, and so this stereocenter must be S. And same thing here, if you put the hydrogen over here, you're going to stick your thumb up. The chlorine's number 1, so it's kind of over here. And then when you curl your thumb, you're going to get to the regular alkane. So you go from 1 to 3. That's not how you count. You don't count 1 to 3. You count 1 to 2. And so again, this is also telling us that it's S. Finally, let's go ahead and take a look at this stereocenter right here. I can zoom in. I forgot about that. So we can draw dashes for our H, and then again we can number things. Chlorine gets number 1, haloalkane gets number 2, regular alkane gets number 3, and then hydrogen gets number 4. And so what I want to do is stick my thumb into the back of the board and then curl my fingers. I'm counting from 3, 2, 1, right? Can't really stick my finger back there that much, but 3, 2, 1. 3, 2, 1. Right? That's not how I count. That's reverse of counting, so this is S. And then you can try the same thing here. We put this hydrogen down here. So I have my H here. Here's number 3, number 2, the haloalkane, and then finally the chlorine, because my fingers are like this, 1, right? 3, 2, 1. And so again, this is S as well. So you see, you can use this picture, you can use this, and again, you can also use the modeling kit. So here we have our model of this guy right here. Right, you can see these are the 4 hydrogens that are kind of parallel right there. And then you can see this one in the front is pointing up. This one in the back is pointing down. And then our 2 chlorines are equatorial. Right. And again, if I stick my thumb up, the chlorine here is number 1, 1, 3. I don't count 1, 3, so that's S. My thumb's down here. Here's number 1, here's 3, and then 2, right? So 3, 2, 1. 3, 2, 1. That's not how I count. That's S, right? So you can use any method that you want. And so let's go ahead and think about the stereochemistry, or the relationship between these compounds. So I'm just going to erase away some of this stuff. Whoops. Erase the wrong thing there. Both R, R, S, S. And so we can see our stereoisomers have both flipped, right? This went from RR to SS, and they're in the same conformation, so they went from wedge to dash, dash to wedge, right? And so these should be, according to this picture, should be enantiomers. Right, but remember, enantiomers are non-superimposable mirror images, and so if we look at these 2 compounds, they don't really look like mirror images, right? Again, here we have our chlorines, 1 and 2, both up and then down. And then here we have our chlorines, right? Same kind of configuration, same way we're looking at it. Chlorine is down and equatorial, and then this chlorine is up and equatorial. And so these 2 don't look like mirror images of one another. But remember, this is not the most stable conformer of this cyclohexane, right? It'd be much more stable if we did a chair flip and then made both of these equatorial. So let's go ahead and do that. And so we can do a little chair flippity flip, right? We can move one of them down, one of them up. And then, of course, what we have to do is change our point of view to really make it look right. Right, so it kind of look more like this. So again, you can see that this would look like this, right? There's the 6 carbons. This one's pointing down, this one's pointing down, this one's pointing up, this one's pointing up. And now you can see our chlorine is coming out of here. And then here, right? They're both equatorial, and you can see the chlorine's pointing out of there. All right, now let's think about the relationship between this conformer, and remember, this is the same molecule, just in different conformers. If I take my hand and make a fist, it's still my right hand, right? So that the identity of this molecule didn't change with this ring flip. It stayed the same. And then let's think about the relationship between this conformer and this molecule, right? What's the relationship here between these two? If we look up above, right, we flip both R and S's, right? R went to S, and so we said that they were enantiomers of one another, right? Non-superimposable mirror images. However, these two, when you look at these pictures, they don't exactly look like enantiomers. And so let's take a look at them. So again, on this left side here, I've got the molecule right here. You can see the chlorine is equatorial. That's this chlorine coming out of here. And then this chlorine is also equatorial. And that's this chlorine coming out of here. So that's that model. And then over here, we have this model right here. We want to view it like so. So you can see this carbon's pointing up. That's this carbon in the back here, or in the front here. This carbon pointing down is this carbon in the down position there. And we can see we have equatorial and equatorial chlorines. And so let's first off see if they're mirror images of one another, like my right hands are. And if we align them a little bit, right, we're just going to rotate them a bit. We can indeed see that they are mirror images, right? You have these chlorines kind of coming together. You have these chlorines coming together. You have these hydrogens popping up. And then you've got the rest of the molecule in a perfect mirror image. So even though it doesn't look like mirror images here, it does here, and it does in real life. You just need to rotate this molecule a bit. Now the question is, are they non-superimposable, right? I can't superimpose my thumbs. Can I superimpose my these molecules? And so if I try to do that, right, try to rotate this 180, you'll see it does not superimpose, right? This hydrogen here is pointing up. This hydrogen here is pointing down. So we can't do that. And then what if we try to flip it like this, right? We still can't do that, right? This hydrogen is still pointing up. So there's no way to superimpose them, so they are indeed enantiomers. So when it comes to cyclohexane, it's actually easier to use this than it is this, in my opinion. So I would recommend that you kind of stick to this, although there is one tricky case that we'll go over next. All right, so let's continue looking at this 1,2-dichlorocyclohexane. And so we've taken a look at these two and decided that they're enantiomers, right? But there's other ways you could draw this flat structure. You could do wedge, and then dash, dash, right? So are those two enantiomers? Are they diastereomers? Are they the same compound? What are they to each other? And again, we can figure out the R and the S configurations. So there's a hydrogen here. Whoops, my bad. These are chlorines. It's hydrogen back here. And then for this one, the chlorine gets number 1, the halo alkane 2, alkane 3, hydrogen 4. We stick our thumb in the back, we count 1, then we curl in, we go to number 2, and then we keep curling, we go to 3, right? So this is the way we're going, and so you can see that this one is R. And then for this other one, right, we stick our hydrogen in, or our thumb in the back of the hand, right, because that's where the hydrogen is, and then we curl this way, right? So if we're thinking about going this way, the way we're rotating is something like this. Right? And if you think about it, this is number 1, this is going to be number 3, and this is number 2, right? So we don't count 3, 2, 1, and so we don't go this way, and so this is S. Cool. Now let's go ahead and take a look at this one. So in both of these, we have hydrogen sticking out. And again, so I'm going to stick my thumb out. Chlorine is number 1. Regular alkane is 3. Haloalkane is 2. 1, 3, 2. That's not how you count. This is S. And then over here, hydrogen sticking out. Chlorine is 1. Haloalkane is 2. Regular alkane is 3. 1, 2, 3. That is the way we count. This is R. And so it looks as though these R and S's have switched. And so it might look like these are enantiomers. But we have to be really kind of careful with these compounds. And we can also think about it in the chair conformers. All right, so I'm going to label this 1, 2, 1, 2. In this case, they're both pointing up. So this chlorine is pointing up, and then this chlorine is pointing up. And here's my model of that. So you can see this front carbon is pointing up, this back carbon is pointing down. And then we have our chlorine up as axial, and then our another chlorine that's up, but this time it's equatorial. And then we can do the same thing over here. We can label this as 1 and 2, and so our first chlorine is pointing down. So this chlorine is equatorial, and then the other chlorine is pointing down as well, so this chlorine is going to actually be axial, right? Because the axial position is down here. And here's my model of that, right? 4 carbons, front one in the front, back one in the back. We have an equatorial chlorine in the back here, and then an axial down chlorine in the back, but they're both down. You see this hydrogen is up, so this chlorine is down. This hydrogen is up, so this chlorine is down. And so let's think about the relationship between these two molecules, right? And so if I'm looking at these two molecules, can I superimpose them, right? Can I first see if they are mirror images? And so if we move them around a bit, we should be able to see some mirror imaging. I might have to do a little chair flip here. It's going to be in the same conformer. We can see that they are indeed mirror images of one another. All right, sorry about that. The phone's battery was dying down. And so, right, we chair flipped this one, and now we can see whether or not they are mirror images. And you can see that they are, right? The chlorine's pointing up here, the hydrogen's pointing down, and then these chlorines pointing up, and then these hydrogens pointing down, right? And so they're mirror images of one another, so that fits the first criteria of being an enantiomer. Now let's see if we can superimpose them or not. So let's go ahead and just move this guy and just rotate it 180. Right, doesn't look superimposed there. Let's rotate it some more. It was superimposed, my bad. And so we can, actually, first we'll need to chair flip this back, right? Not superimposed. Not superimposed, right? It's not superimposed anyway. And so we'll need to chair flip this guy right here. So just flip 2 of the carbons. Sorry, this model kit's not quite the best, right? Chair flip them, and then let's try to superimpose them now. And if we try to superimpose them now, we will see that they will indeed fit. Carbon should be pointing down more. Right, they do indeed superimpose, right? Chlorine up, hydrogen's down. Chlorine's up, hydrogen's down, and all the rest of the carbons are the same. And so these two are not enantiomers. If you think about it, there is indeed a plane of symmetry bisecting this molecule, right? If you put a plane there or a mirror there, there's a mirror image right there. And so this is what's known as a meso compound. And so these two are the same molecule. And so 1,2-dichlorocyclohexane only has 3 stereoisomers. It has this pair of enantiomers, which is 2 molecules, and then it has 1 meso compound, right? This is the same thing. And then the relationship between these 2 enantiomers and this 1 compound are that they're diastereomers. Right? They're non-superimposable, but they're not mirror images. And so For the cyclohexane stuff, it's probably easiest to just stick with the flat drawings. They'll give you pretty much the same information as the chair when it comes to whether the enantiomer or meso compound or relationship between these compounds.